Problem number 3 basically laid out an RC circuit, resistor here, capacitor here, and then a neon gas tube here. And the battery charged the capacitor and charged it until its potential difference was great enough that it could ionize the gas in the gas tube and then discharge through the gas tube. And that happens over and over again. And the discharging through the gas tube, it said, was basically instantaneous. So we can think of it as just a charging and charging and then just a pop. And discharging, lighting up the gas tube, and then once the potential difference is small enough, it can't ionize the gas in the tube anymore, and then it continues to charge. So they gave us a really good visual representation, a graph of basically the potential difference of the capacitor here. So this is it charging, 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 and then it gets to this point, and then it discharges. So basically, an important differentiation that I have to make here is that capital T represents the amount of time that it takes for the capacitor here to charge fully and then discharge, and then little t, or lowercase t, is basically represents the x-axis, or any point t that is on this graph. So this point t represents a point where basically, well, it could be either V on or V off, but represents the point where the potential difference in the capacitor is at its lowest. So it's just after it's discharged and it's starting to charge back up again. But if you had this T, which is down here, this would be right before it discharges. So this would be at basically its highest potential difference. So basically, the question asks us to use the equation, which we actually know from learning it in class, that delta VC, which is the potential difference across the capacitor t at time t, is equal to E1 minus E to the negative t over RC, and show that the period of oscillation is t equals RC natural log of this. So I started off by, you have to break it up into two parts basically. So you have delta VC on, delta V capacitor on, and delta V capacitor off. So the only difference, like I was talking about, is between just having T and having T plus capital T, which is that difference between the fully discharged, not fully, but the discharged capacitor, and then having it be a little bit more charged and more charged and more charged till it's almost at its point of discharging through the gas tube. So once you have delta V C on is equal to E times 1 minus E to the negative T, which is that point on the x-axis, plus T, capital T, which is that distance between the basically one kind of period length of the charging and discharging over RC, as opposed to delta VC off, which is which the only difference has this capital T missing. And then you solve these for T basically in the exact same way. We can divide by E first to get E on this side. Then this was kind of two steps, but I took the 1 over minus 1 on both sides, and then I just multiplied everything by negative 1 to make it look simpler. And then use the natural log to bring this down, because e to the thing, you just use natural log to get something equal to the thing. So then you just solve for T by multiplying both sides, in this case multiplying both sides by RC, and then there was one more step on this side because you had to, remember this is negative, that should be negative T plus T. This negative should be outside the parentheses because both of these are technically negative, not just the first T. So I added this T to both sides to get T plus RC natural log of this equals negative T. Okay, so then you have negative T equals a thing, and then negative T equals a thing. So once you have both of these, then you can set them equal to each other and solve for this capital T, which is that time. Remember that time that it takes for the capacitor to charge and charge and charge until it discharges. So we have RC natural log 1 minus delta VC on, and then RC natural log 1 minus delta VC off. So it's pretty simple from here on out. All you have to do is factor out the RC, and then once you have this expression, we just know that natural log of x minus natural log of y is equal to the natural log of x over y, so we can rewrite, and then also, well, okay, I'll see this in a second, of x over y, so we know we can rewrite this as a quotient. T equals RC natural log of 1 minus delta VC off over E divided by 1 minus delta VC on over E. And then because 1 can be rewritten as E over E, we can just cross out the, I didn't write this step, but we can just cross out the denominators, and then we have E minus delta VC off over E. Well, it's actually right here. E minus delta VC on. And then this piece of this page came out so oddly shaped because when I scanned it, it didn't scan the whole 8.5 by 11 piece of paper, it just scanned the part with writing on it. So that's why this looks so strange. But this is the only part with writing. So this is the final expression, and that's how you get the answer.